Thanks a lot for the organizers for allowing me this opportunity. I'm very happy to be here and to celebrate Jeremy Castell's birthday. I think I know Jeremy a bit less than other participants of this conference, but let me mention one point of contact. There is the famous paper of Amir, Corwin, and Castell, maybe 2011, and I had some role in the authors of that paper. I was in the Courant Institute when Ivan was working on these questions, and I visited Toronto and I learned that Gidi and Jeremy are working on these questions, and I played the matchmaker, and it seemed to work out well, and even acknowledged there. Okay, so I hope Jeremy will like this talk and also all the other participants. In this conference, I think many of the talks focus on geodesics or polymers in 2 dimensions, and maybe some of them talk about geodesics or polymers in higher dimensions. In this talk, we will also do that, but also focus on something somewhat new that maybe nobody almost considered before, which is the idea of minimal surfaces in a higher dimensional random environment. So instead of geodesics, which are pads, this will be surfaces, kind of full surfaces. And there isn't much in the mathematics literature about that, although there is extensive physics literature on it. So here we see some pictures of this kind. This is the usual one-dimensional path in a 2-dimensional environment. This is like first passage percolation in 2 dimensions, for instance. This is, again, of the same kind. It's a bit hard to see, but this is supposed to be a path in a 3-dimensional space. Throughout the talk, there will be 2 dimensions. D is the dimension of the surface, because it's a path. D is 1. It's a 1-dimensional surface, a path. And N is the codimension. So because it's a path in a 2-dimensional space, the codimension is 1. A path in a 3-dimensional space is codimension 2. So N is the codimension. You see it here now, N equal 2. And here we see a 2-dimensional surface in a 3-dimensional space. So D equal 2 and N equal 1. So these are the kinds of objects I would like to discuss today. Okay, I have a first motivation slide. I think for this audience it is not needed. There is the notion of first passage percolation. I believe most of the audience knows it. Let me maybe very, very briefly say, when you give the edges of ZD random weights, then that makes ZD into a random metric space. You can now ask, what is the shortest path between 2 points in the sense of the sum of these weights? And that is our first passage percolation. We would like to understand, if you take 2 very far away points, how does the minimal path between them look like? How close is it to being flat, for instance? That's a standard question. Okay, so I hope most of you know this. And now something that maybe most of you do not know, something about surfaces. Let me introduce this through an Ising model and mention that you can also introduce it through a combinatorial type of question. So let me just put the whole slide. So now let's consider the following setup. You have, again, IID weights attached to the edges of the ZD lattice. Each edge has a weight. The weight is positive. This is important. It is positive. For instance, uniform between 1 and 2, independently between the edges. It's going to be a random weight. And now I consider an Ising model. Just, I hope everybody is familiar with the Ising model. I mean that I assign each vertex either -1 or 1. And I calculate the energy of the configuration by saying that for every edge, I multiply the spins at the endpoint and also multiply by this random weight, by the weight of the edge. So the weights of the edge are the coupling constants. This means that the Ising model wants adjacent vertices to be equal, but it wants to do so more strongly if the weight of the edge is large, and more weakly if the weight of the edge is small. And the weights are random, so there are bonds, specific edges, where it's easier for the Ising model to put a domain wall, to put a difference plus next to minus. Okay, and we would like to understand how large domain walls look like in this so-called random bond Ising model or disordered Ising ferromagnet. And one way to get a large domain wall, we're doing everything at 0 temperature, so we just ask for the minimizing configuration. One way to obtain a large domain wall is to use Dobrushin boundary conditions. So you take a large cube, and you put plus boundary conditions on the top half of the cube. So you put plus boundary conditions here, minus boundary conditions here, and you ask for the configurations of pluses and minuses inside, which has minimal energy. Necessarily, there is a domain wall between pluses and minuses, and that domain wall needs to find, in some sense, the weakest bonds, the bonds such that the sum of edge weights will be minimal among all the ways to cut this cube into two parts. And indeed, so some surface will form like that, like in the picture. And indeed, you can also think of this combinatorially. You're trying to find the minimal cut separating the upper and lower halves of the boundary in this network where you assign each edge a random capacity uniform 1 to IID, say. So it's really a minimal cut problem. If you do it in 2 dimensions, like so, then in fact, this minimal cut is just going to be the first passage percolation geodesic in 2 dimensions that we're familiar with. But in higher dimensions, it's something else. And we have studied this in recent work with my former student Michal Bassan and colleague Shoni Gilboa. But let me get back to that later in the talk. So these were 2 motivational slides. There was first passage percolation, that is about geodesics. And there was minimal surfaces of this type with this Ising model. But what will I actually talk about? I'm going to study a third model, which appears to be more amenable to analysis. So what I would like to introduce is a model for more general d-dimensional surfaces, d-dimensional minimal surfaces, in a d plus n dimensional random environment. So we have a dimension and we have a codimension, d and n. But if you don't like the codimension, if you don't like 2 parameters, you can think of the case that d equal 1, that will be geodesics in whatever space, or that n equal 1, that will be surfaces with codimension 1, if you prefer. Okay, so what is this model that we found, which was actually well known in physics, but not so well known in math, although there are works I will explain in the next slide. So the model is the following. Let me, as I talk about it, also introduce it on the side. So we'd like to model surfaces. Let's first draw a 1-dimensional picture. So in 1 dimension, let's do d equal 1 and n equal 1. So I'm just trying to think of something like the geodesic from this point to that point. This is an interval of length L, say. I want to go from here to there. If it was first passage percolation, my geodesic could go back and forth, and my geodesic would be restricted to lattice points. I'm going to do some approximation. I'm not going to allow the geodesic to go back and forth. It's going to be a directed model. And I'm also not going to restrict it in their heights. My geodesic will take values in R at every vertex. So I draw here a copy of R at every vertex. And my geodesic is going to be defined by a function. Surface is going to be defined by a function phi from ZD to Rn. So in the case that d equal 1 and n equal 1, it's just going to be a function that chooses a number on these real lines at every vertex, like so. And I'm going to give it boundary conditions. In this case, I specified that it starts and ends at the height 0. So my surface is this kind of object. It is not constrained to integer heights, and it is directed, so it doesn't have overhangs, to speak. My disorder, the environment in which this lives, This is going to be a function, an arbitrary a priori function that is assigned to each of these fibers. So at every vertex, I have the fiber, the copy of R, and at every copy of R, I have a function. So this function is a function from dv times Rn to R. Sometimes it's nice to think of R union infinity. And the way it goes is that my geodesic would like to pass through points where this function is low. This function will be a potential energy for my geodesic. Let's also show a higher dimensional picture to have additional sense of what's going on. So let's say d equal 1 and n equal 2. So this means the geodesic in three-dimensional space. So that means that at every vertex, I have a copy of R squared. And on every copy of R squared, I have a general function. And then my geodesic chooses a point in R squared at every vertex. And if it is surfaces, d equal 2 and n equal 1, say, then I have some base domain composed of vertices. And at every vertex, I again have a fiber like that. And at every fiber, I have a function. And my surface chooses the height at every vertex. Okay, it's a bit hard to draw. I hope you can get it from the definitions here. So this is the surface. This is the disorder. It is convenient to have a strength parameter, but if you don't like, you can just set it on lambda greater than 0. And then the way that I'm going to define my minimal surface will be the minimizer of a certain energy functional. The energy functional contains two parts. There is the elastic energy of my surface, and there is the environment potential energy of my surface. So let me write it down because it's nice to have it during the talk. So this is my energy functional. And let's just explain what is going on here. So my geodesic, as I mentioned, or my surface can jump to any height. So when it goes between two vertices, for instance, when it passes from here to here, it's going to measure by how much did it change, and it's going to pay for the jump. The payment for the jump is quadratic. And then, in addition, as I said, it's going to pick up the blue function. It's going to pick up the disorder at every vertex that it passes. And you want to minimize this on a given domain. My domain in this stuff will always be lambda L, which is minus LL to the D. So I'm always going to think that it's living above a cubic basis of side length L. And it has some boundary conditions. We will see that these are not, but in this talk, they will always be set to 0. So I have a geodesic. In the absence of disorder, the minimizing surface will be completely flat, a geodesic or surface. And in the presence of disorder, it might be fluctuative. And our goal is to study how fluctuative, how far from flat is it. If you're in d equal 1, n equal 1, then this should be the usual L to the 2/3 type scaling that we're familiar with. This should be in the same KPZ universality class. Beyond that, it's an interesting question too. What is it? Okay, so this is the introduction of the model. I hope everybody understands what it is. If not, please ask me. As I said, this model has not received much attention in the mathematics literature, but it has received attention in the physics literature. Let me briefly say what I know of the mathematics on this. So in mathematics, there is a series of works by Yuri Bakhtin and the co-authors. However, all of them deal with the case d equal n equal 1 in connection with the Burger's equation. So they definitely studied this model, but in the restricted setup of 1 + 1 dimension. Correct me if I'm wrong, Yuri, if he's here. There is a literature on Brownian polymers in a random environment, and that's also related. This is like the positive temperature version of this with some environment, depending on whether it's directed or undirected. If it's directed, then it's like this. And very recent, somewhat recently, there is also work of Benner, Roos, Bourgade, and McKenna under the name of the elastic manifold, and following work of Pierre Ledussal and Jan Fyodorov, where they do indeed study this model for general DNA. However, they do not talk about the same sort of questions. They study what is called landscape complexity, the number of minimizers rather than the geometry of minimizers. And moreover, they take n to infinity. So they don't study it for a fixed value of n. But later today, Gerard will tell us about additional work on this model, so we will learn more. And in the physics literature, as you can see, there is a lot of literature going back and even several reviews of this. Okay, so how to work with this model? First, in order for me to say anything, I will have to specify what is the disorder. The disorder is a quenched random environment, but I have to specify from which distribution. Now, motivated by the examples in the beginning, the most natural for me is to consider disorders which are, so to speak, independent. I want to make them short-range correlated, as white as possible, so to speak. Now, looking at this picture, there is no problem to make the blue functions independent from vertex to vertex, from fiber to fiber. But of course, on a fiber, I cannot make them IID. It's a continuous process. I have to do something. So our main example in this talk is this one, a smoothed white noise. So what this means is that the functions are IID between vertices. And in each vertex, what you have, you take a white noise on this fiber, and you convolve it with a bump function to make it smooth. So just smoothed white noise. It gives you a certain range of dependency. So on every fiber, I have my white noise, and I'm convolving it with a bump function like this. The bump function is going to have width 1, and that gives me a certain range of dependency, 2 in this case. Okay, so this is our initial focus. Later in the talk, I will also talk about other disorder distributions, their motivations, and some results. But this is the initial motivation. Let me say that many of our results are proved under more abstract assumptions that go beyond these examples. The abstract assumptions hold for this example, but they allow for a much more general class. In particular, what we need, there is some independence in some of the results, not all. There is a certain concentration of the ground energy, which is like a Talleyrand's estimate or Hoeffding's estimate. So the kind of a priori bounds we have in first passage percolation, that if you are talking about the geodesic of length L, then the standard deviation of the length is at most square root L. This kind of a priori upper bounds is the concentration assumption. And there is a certain stationarity. It will be useful in many of the results, in all of the results, that the disorder is stationary under shifts up and down, and these shifts can even be carried out independently between vertices. Each one has its own shift. So stationarity, independence, and concentration. Let me emphasize, because this will come up in some of the results, that if I only have stationarity and independence, you will see that when I speak of a scaling relation, then this even allows me to vary the disorder strengths between vertices. So it could be that some vertices have a very strong disorder, others have very weak disorder. So this allows for a wide variety of disorders. And later I will talk of periodic disorder, and these assumptions hold for it, but that's for later. Okay, so now I've described to you the disorder. We will focus on independent disorder, and our main example is smoothed white noise. Let me now describe the results that we can get for this model.
This concentration
assumption,
is this easy to verify?
Well, it's not hard to verify for smoothed white noise. it comes out of Gaussian concentration. So it's kind of the basic Gaussian isoperimetric inequality, or manifestations of it. If the disorder is bounded, you can even get it from Hofding's inequality. So this is a relatively weak, so to speak, a priori assumption. But of course, because it's not sharp, because it doesn't have the correct scaling, some of our results will also not be sharp. And if you could improve it, it would actually improve the result. But to start with, all right? And again, it's verified in this example. So you have a concrete example. Other questions? Okay, so what do we want to study? As I mentioned, our interest is to measure how far is the geodesic when I work in this box, minus LL to the D with zero boundary conditions. So how far is the geodesic, or how far is the surface from being completely flat? And as we mentioned, if we do it in 1+1 dimension, we may expect the deviation from flatness, this deviation, to be of order L to the 2/3. That's what it is in the 1+1 dimensions. We actually don't know how to prove it for this model, but we may expect it. What will it be in higher dimensions? What will it be for surfaces? Is it a power of L? Is it a logarithm of L? Is it order 1? Is it something else? These questions are a priori not known, and we have some answers. So here is the answers regarding localization and delocalization. We have a result on localization. We have a result on delocalization. And let me first put a table that summarizes the results for the case of n equal 1. So for the case that you have surfaces of codimension 1. So as described, it should be L to the 2/3 in 1+1 dimensions. Our lower bound is L to the 0.6, and the upper bound is L to the 0.75. In dimensions 2 and 3, so two-dimensional surfaces or three-dimensional surfaces, there are numerical simulations in the physics literature. There are also functional renormalization group argument, also replica symmetry arguments. But here I've presented the numerical simulations, which give these values for the fluctuation exponent. So the physicists tell us that it should be power law delocalized. We are able to prove that it is power law delocalized in the sense of lower and upper bounds, which become tighter as the dimension increases. So which should be 0.41, we have 0.4 and 0.5, should be 0.22, we have 0.2 and 0.25. As it turns out, four-dimensional surfaces are critical in these models. It is predicted that the delocalization of the surface is sub-power law. It is delocalized, but not to a power. In fact, I found the prediction log L to the 0.4166 something for this surface. And we have, indeed, we're able to show it's sub-power law delocalized somewhere between log and log-log. In dimensions greater or equal to 5, these surfaces are localized. They have order 1 fluctuations at a vertex. All these results are new in the surface case. In fact, they are new even when d equal 1, even for the geodesic case. For the geodesic case in the non-integrable models, there was no L to the 3/5 lower bound. This result was known, but there was no L to the 3/5 lower bound for point-to-point. There was a point-to-line in the work of Bachten and Wu. And here I will explain something about n greater or equal to 1, n greater or equal to 2. Let me get back to that. Okay, if you want to see more details, then this is the upper bound is a pointwise bound on every point. We also have results on the maximum. We have a law of the iterated logarithm sort of bounds and law of the fractional logarithm sort of bounds. And the lower bound, we cannot get it pointwise. We cannot say that at every point it is likely that the surface delocalizes. This is analogous to the so-called midpoint problem, and sometimes Binyamin Nikolai Schramm midpoint problem for first passive percolation. We do not present a solution of that here, but we get that, say, 1% of the points exceed the value h, and the value h is given by these formulas. Let me emphasize that in the geodesic case, d equal 1, we can show that the geodesics are always at least diffusive. At least square root of L. So this is again something predicted by in the physics literature. There is an ongoing debate in the physics literature whether there is any co-dimension n such that the fluctuations are exactly square root L. We're not at this point able to settle this debate, but we can at least show that it's at least square root L. Again, this is a new result. In a somewhat weaker sense, Chuck Newman had shown that the geodesics have fluctuations square root L, but that was for almost geodesics in almost every direction, so it wasn't like this. Woodrich has shown for Brownian motion in a Poissonian environment a bound like that, but that was at positive temperature where it's a bit easier, and point to line, I think. So again, these are new results even for d equal 1. Okay.
So that's the lower bound?
This is the square root L lower bound. That's right. The upper bound L to the 0.75 was known, for instance, in the works of Yuri Bakhtin with co-authors.
Higher dimension?
It was not, I think, explicitly done in for n greater than 1. Right. And all of the d equal 2 results and higher are completely new, it appears. Okay, so these are our results. Again, this is joint work with Barbara Dembin, Dor Elboim, and my student Daniel Hadas. These are our results on localization and delocalization. We also have a second set of results that I will now present. So these are our results on a scaling relation. So what is the scaling relation? So the slide introduces it, but let me also write on the board. We have these transversal fluctuations as described here. Let me write them as a power L to the psi. Naturally, psi depends on the dimension and the codimension. There is another fluctuation exponent. I can speak of the minimal energy. The minimal energy we like to denote by GE. GE for ground energy. So this is the value of the Hamiltonian at the minimum, given the boundary conditions. And there is another fluctuation component I can consider saying the standard deviation of the ground energy. In fact, I will argue that it is not clear standard deviation is the right thing to take, but for purposes of explanation now, let's write that and say maybe that's like L to the chi dn for another fluctuation exponent chi. Then people familiar with the KPZ universality class are familiar with the relation that chi equal to psi minus 1. As it turns out, in the physics literature, already going back to the work of Hughes and Henley in 1985, there is an extension of this relation to higher dimensional surfaces. So Hughes and Henley proposed that chi equal to psi plus d minus 2, where d is the dimension of the surface. This naturally makes more sense when the surfaces are in dimension 1, 2, and 3, because then they actually are power law delocalized, whereas in higher dimensions they are not. Okay, and we obtained rigorous versions of this equality for general D and N. Let me now present these versions. So let me write average for the average operation, the average height of the surface. GE, as we said earlier, is the energy of the minimal surface. Here is a first version. These results are obtained under only stationarity and independence assumption. So they hold uniformly, for instance, in the disorder strengths, even varying disorder strength from vertex to vertex. They hold for a very wide variety of disorders. So here is a version of the direction chi is at least 2 psi plus d minus 2. Let us measure the deviation of the ground energy from its median. Well, and let us measure also the average of the minimizer, the average height of the minimal surface. Well, if there is a chance for the average height to be bigger than h, then there is a chance for the ground energy to deviate from the median by h squared L to the d minus 2. So if I plug in this result h equal L to the psi, where I may expect this to be of the order, say, 1/10, I don't know, a constant order, then here I will get L to the 2 psi plus d minus 2. So exactly chi is at least 2 psi plus d minus 2. Let me emphasize this holds, again, for any disorder strength, but let's also emphasize this holds without any logarithmic corrections. So it is a more precise version than this, which only holds on the level of exponents, no logarithmic corrections. In addition, it holds not only in the bulk of the distribution, it holds even in the tails of the distribution. You can take h to be extremely large, and this gives you a relation. So it's much more detailed than the basic equality. This is one direction. Here is the other direction. In the other direction, we would like to say chi is less than 2 psi plus d minus 2. I'm going to do it in a bit of a different way than you may a priori imagine. What we're going to do, we take our domain, and we take a concentric subdomain, and we will resample the disorder above the vertices of the concentric subdomain. So if I draw a one-dimensional picture, we're taking the middle part and we're resampling the disorder, all of the blue lines on this middle part. Okay, and now we will compare the ground energy before and after resampling. Then again, this time I will measure the height fluctuations by the maximum. We also have a pointwise version when d is 1 and 2, better than maximum. So if it is unlikely that the height of the surface exceeds h, then it is unlikely that the ground energy fluctuations exceed h squared L to the d minus 2. Again, this is for all disorder strengths, all values of n, the codimension, all values of dimension, and also in the tails of the distribution. One may complain that when doing so, I have not really caught the standard deviation of the ground energy because I've only resampled the distribution in the middle and not everywhere. In dimension 1, we go for a more refined result where we allow ourselves to resample the distribution everywhere, and we obtain as a two-sided bound that the energy fluctuations are controlled by the height fluctuations, but you have to treat differently the height fluctuations close to the boundary than you would the height fluctuations in the middle. And this is a two-sided bound. That is, you do in fact have to do it. So in fact, when people speak of this relation, does it work? Okay. When people speak of the scaling relation, it really measures how the bulk fluctuations are related to each other. If the boundary fluctuations are important, then those boundary fluctuations will change the scaling relation. At least we prove it in dimension 1. In dimension 1, it may be that the boundary fluctuations are not so important, but I believe that in dimension 2, they could be important, even without varying disorder strength or anything like that. In one dimension, they could be important if the boundary disorder strength is larger than the bulk disorder strength. Okay, so we have these versions of the scaling relation. Again, joint works with Dor Elboim, Barbara Dembin, and my student Daniel Hadass. Let me mention that the scaling relation is also a new result. When d equal 1, there were proofs of it under unverified assumptions, first by Wootrich in '98 for Brownian motion and Poissonian environment, then by Chatterjee, then by Damron and Uffinger. But all these under unverified assumptions. This does not have unverified assumptions, of course, though it is for this model. Very recently, at the same time as our paper, there appeared the paper of Basu and Sly, which proved the scaling relation when d equal n equal 1. However, for certain rotationally invariant models under assumptions that will be verified in a sequel paper, but it will be without assumptions. It's just not yet published without assumptions. Okay.
So for this, what kind of variance bound can you get on the velocity energy?
Say again, what can you?
What kind of bound on the variance
of the ground energy. Very good. So once you have the scaling relation and you have what you had in the previous slide, sorry for going a bit slow here. All right. And you have the bounds on the height presented in the previous slide, then you can transfer these bounds on the height to bounds on the energy. To be more precise, we're able to make this transfer exactly when d equal 1. We're able to make this transfer exactly, but with a logarithmic loss when d equal 2. And for d equals 3, we're not exactly able to make this transfer because for d equals 3, we're not able to control the average height of the disorder sufficiently to make use of this. So for d equals 3, there is a bit of a gap between our height fluctuation result and our energy fluctuation result. However, you do get lower bounds on the ground energy, even for d equals 3, through other mechanism, but it's slightly worse for d equals 3. Okay. All right, so I don't have much time, so I'm not going to tell you anything, unfortunately, about the proof, but I will at least convey the following information. There is a main identity which relies on the fact that we have a quadratic energy over here. It's an easy main identity. It's just these 3 lines, very simple deterministic identity. It implies things like the limit shape being exactly a quadratic limit shape. So it implies limit shape as you would like it. It also implies for the surface cases that if you put boundary conditions which are not 0, then all that does is add the harmonic extension of the boundary condition to your model. So it's something that is familiar for people that know the Gaussian free field. And it is the thing that we use everywhere. So it extends the so-called shear invariance to harmonic invariance. But it is important that we use this identity even when S, the shift, is not harmonic. Okay, and once that is conveyed, all I can say really is that if you want very basic versions of localization in one direction, that's very basic versions are not that hard, presented here in 2 slides. Of course, I also say that to obtain more sophisticated versions, you have to work more. But 2 slides from the main identity to get simple versions. A bit more complicated, 2 slides but with small font to get delocalization. So this is really presented just so you get some feeling. These are again the basic versions. If you want the more sophisticated versions that we have, it's longer than that. So this was 1 slide and this is a 2nd slide. Okay, that's all I'm going to say about the proof. Didn't say much. In my remaining 2 minutes, let me go back to domain walls in the disordered Ising ferromagnet. You remember that from the beginning, this was this model that is explained over here with the plus and minus boundary conditions. You can ask, do our results reflect the actual fluctuations of these interesting models? Well, we believe they do to an extent. There is also some interesting deviation. So now we will take the weights, the coupling constants, to be uniform AB for B greater than A greater than 0. In joint work with my former student Michal Bassan, now a PhD student in Oxford, and my colleague Shoni Gilboa, we show that if B minus A over A is small, so if this is, for instance, uniform 1, 1 plus epsilon, so it's a concentrated distribution, then the surface is localized when small d is 3. So this is a different behavior than this model here, which delocalizes for d equals 3. We think that that is only because this surface here is constrained to take integer heights. So we think that the integer height constraint changes the behavior of the model, changes the limit shape from strictly convex to having a cusp in that direction. If the distribution is small, is concentrated in dimensions 3 and higher, but not in dimensions 1 and 2. So we have, and there was an earlier results by Bovia and Kulska on a related thing on the disordered solid and solid model. And we have a conjecture for what happens in higher dimensions. We think that in dimension 3, there is a phase transition. When the disordered distribution is not concentrated, we think there is a roughening transition. The disorder strengthens, suddenly it goes back to behave like this model.
Surface is not actually a surface, right? It's an over.
I think the reason for quotation mark is that I copied it from the initial slide. And in the initial slide, this may have been the first time that I spoke of the concept of minimal surface. So I wanted to give it some highlights. Sorry about that. I should change it. It can have overhangs. And in the theorem with Bassan and Gilboa, the main difficulty that creeps up everywhere in the proof and makes our life very annoying and hard is the fact that it can have overhangs. So we are really analyzing the actual overhanging surface here. And that is what makes it much harder than, say, the result of Bovia-Kulska on the disordered Solden-Solomon. Thank you for the question. Okay, in the non-existing time that I have, let me mention that we are also interested to study Brownian disordered, motivated by physics. If you do exactly this construction, but for the random field Ising model, rather than the random bond Ising model, then you should get something like this model, where eta is a two-sided Brownian motion. In fact, that model is analyzable. In a sequel work in preparation with Barbara Denbin and Dor Elboim, we consider even more generally fractional Brownian disorder with Hertz parameter h between 0 and 1, and the height fluctuations then have an exact, easy to compute, well, easy to write formula. They're exactly L to the 4 minus d over 4 minus 2h in dimensions d equal 1 to 3, uniformly for all values of n. They do not depend on the codimension. And we're able to prove that in a sequel work. And this was predicted also in the physics literature. There are other interesting cases of disorder. Periodic disorder has to do with the random field XY model. Our localization results apply to it. So we get in particular that it's localized for d greater or equal to 5. Let me not get into it. Linear disorder is something the physicists sometimes call the random rod or Larkin model. It's exactly solvable. But even for that simple kind of toy example, we do not know to resolve the conjecture of the roughening transition in 3D. We only have one side of it. Okay, that is all. Here are some selected open questions, to some extent discussed in the talk. Thank you very much.
Questions? You were looking at the ground state. If you look at a positive temperature version, similar exponents.
So, right. So we haven't tried at all the positive temperature version. When the disorder strength is constant, lambda is 1, I would expect the results to be the same. I don't know for sure. Maybe at high temperature, they might be a bit different, right? Because there are these continuum. But this is something I'm a bit struggling with to understand exactly. Maybe it's really the weak disorder. Maybe it's important to take strong enough disorder if you take high temperature, and then it should be the same. If you take weak disorder, I think, from what I've been looking at, that maybe the height fluctuations could change. For instance, we know from the continuum polymer that if the disorder strength is L to the minus a quarter, the height fluctuations are square root L. But I think that in the 0 temperature case, they might not be. Maybe they are L to the 5 over 9. So maybe in the weak disorder regime, there are differences in the height fluctuations as you turn on temperature. I don't have a good understanding of this fact, if it is indeed true.
For your bump function, if you don't assume it's compact supporting, if you assume the bump function decay like power, then can you say anything about the?
If you assume the bump function decays like a power and you convolve white noise with it, then you get long-range correlated disorder rather than short-range correlated. Then it is very similar to what we are doing with the fractional Brownian disorder. We only analyze that particular case. It's very convenient. It has some scale invariance, but it may be that you can analyze other long-range correlated disorders similarly. So you would need so a fractional Brownian disorder actually has increasing correlations. So you would need that. If it's short range, so if it's decreasing correlations but not short range, then I believe our methods should give something, but I've not worked it out. And if it's And in that case, probably they again give upper and lower bounds on the exponent rather than exact value.
Think about it. We're gonna get at 2:00. That's much. Okay, that was. I was like.